we have a 3-methyl group, and then that's going to be a 3-methyl 1-butyne. Telling me we have a triple bond at my position 1, which is a terminal triple bond, and then a 3-methyl substitution. Or we can do it vice versa. So if we look at a molecule, let's say 1,6-heptadiene, so this one is telling me we have 2 triple bond or 2 alkynes. So 1,6 is like going from here. So we start from carbon 1, 2, and keep in mind my triple bond must be a linear molecule. So 1, 2, 3, and then we can start to do our zigzag, 4, 5, 6, and then 7. All right, so the important take-home message when drawing the triple bond is this is always linear. Like if you show something like this is generally speaking not correct unless we're looking at a ring structure. So just remove it. All right, so keep your linear alkyne as linear as possible. Likewise, there are a few common names. For example, if we have, like, say, acetylene, that's going to be talking about we have a triple bond. Yeah, so occasionally we also use acetylene as a form of the common name for the alkynes. Let's say 2-butyne, this is sometimes also called dimethylacetylene. So we're talking about 2 methyl groups on the end of the acetylene molecule. Or this one is 1-butane 3-ine. So that's a vinyl acetylene. So this is a vinyl position, a vinyl carbon, or the carbon neighboring to a double bond. But again, I'm not going to test you on the common names. Just keep in mind people use it when you talk about common names for these triple bond containing molecules. And to add a little bit of complication, which is cyclic alkynes. So cyclic alkynes do exist, but there's a limitation. So typically, when we are looking at cyclic molecules, remember we have ring strands. We were talking about cyclohexene favoring the chair conformation because these carbons you want to have 109.5. And for look at cyclopropane, has a huge ring strand because the ring is confining the carbon-carbon-carbon bond angle. So when we're looking at alkynes, normally the carbon-carbon, these angles, the bond angle, we're expecting them to be 180 degree because of the nature of the sp hybridized carbon. But if we put it in the cyclic structure, it inevitably will undergo a significant distortion. So as a result, the smallest cycloalkyne we can have is at least a cyclo-non-9. So if we count it, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we at least have 9 carbons in a cyclic molecule to have a cyclic alkyne. Otherwise, these molecules are going to be super reactive at room temperature. Like even in the cyclo-non-9, which structure is showing on the right, the actual carbon-carbon bond angle here is about 155 degree, and it's a highly stranded molecule. Yes?
So did you say that's the smallest ring structure you can have a triple bond?
For this class, yes, but as an interesting side note of reading, we have a chemist at UCLA Chem Department who's Neil Garg, and he's very good at synthesizing these strand molecules. So for example, there exists something called benzene that you can transiently synthesize throughout the organic synthesis process and use it for chemical reactions. Now, I mention it not because I want to test you on it, but because I want you to know that beyond the textbook organic chemistry, chemists do play with these strand molecules. So they can be your reactive intermediate. But for this class, when we're writing down a cyclic alkyne, make sure we're writing it in a big enough ring because we don't want it to be super reactive. But still, I want to know what the reality of chemical research is. All right, so these are the properties of the alkyne. Again, several take-home methods, right? One, knowing how to name it. Two, knowing my sp, my carbon on the end of my triple bond is sp hybridized, so we're expecting a bond angle to be 180. If we force it into a ring structure, then we're creating a significant ring strain. So the smallest ring, stable triple bond containing ring is 9-member ring. Physical properties of alkyne, these are pretty straightforward. Like alkene, the alkyne itself doesn't have too much of polarity to play with. So physical property of your alkyne will be very similar to your alkane and alkene, meaning that the only intermolecular forces holding your molecules together are London dispersion forces. So the longer the chain, the higher the melting point and the boiling point. All right, so these are like super straightforward property of alkynes. And now let's talking about chemical properties of alkyne. First thing first, acidity of alkyne. So this should be a quick review in something we discussed before. So what we discussed before, for a general Bronsted acid, remember the Bronsted acid will donate a proton upon dissociation. So the HA will be my acid, and my A- will be the conjugate base. Or more specifically, this is my Bronsted acid. All right. And we were discussing the more stable the conjugate base is, the stronger the acid, or the more acidic acid we're dealing with. So in our trend for acidity, we discussed that more S character on the anionic charge on the conjugate base, the electrons are closer to the nuclei and hence more stable conjugate base. So that means if we're looking at a terminal alkyne or a hydrogen attached to a sp hybridized carbon, that hydrogen is a pretty acidic hydrogen because we're forming the anionic charge on the sp carbon with more S character. All right, so if we're looking at these terminal alkynes, they are pretty acidic molecules. All right, so these are a quick review. Now, how do we use the acidity of the alkyne to prepare different alkyne molecules or to manipulate with the carbon skeleton of the molecule? So going back to what we did with alkenes, remember in the alkenes, we're talking about electrophilic addition, mercuration reduction, hydroboration oxidation, or like oxidation, oxymercuration, right? So all these reactions are manipulating the alkene functional group into different functional group. The only thing that we manipulate the carbon skeleton is ozonosis, where we cleave that carbon-carbon double bond. But in organic chemistry, we also want to extend our carbon-carbon skeleton. So the first reaction we want to introduce, which is the preparation of alkyne, is a nucleophilic substitution. What does it mean? Is that starting from acetylene. So in this case, we're saying sodium acetylene, or you're preparing the sodium acetylene from a simple acid-base reaction. Or your OH minus comes and grab that acidic hydrogen, and we're forming the sodium acetylene intermediate, or that anion, or the conjugate base of your acetylene. Right, just simple acid-base reaction. And then what else? When we're putting this anionic group next to reaction with a haloalkene. Now in the haloalkene, what do we know? We know that the halogen is a partial negative charge because of its electron negativity, and consequently, the carbon next to the halogen will have a partial positive charge. All right. So this is a typical substitution reaction. Now, the arrow pushing will be like this. The anionic charge of your conjugate base attacking the cationic carbon right next to the bromine group, and then the bromine group will leave. What we end up generating, well, if we count it, this is 1, 2, 3, 4, 5, 6. Right, so what's the product coming from this reaction? Well, it's going to be HC, that's my 1. 2, the triple bond is remain untouched. We're not using the nucleophilicity of my triple bond because its anion is even more nucleophilic. And that attached to my carbon 2. Remember, we want to draw it as a linear molecule. So that goes to my carbon 3, 4, 5, 6. And I don't have to show the carbon. I just show this carbon because I want to keep myself, reminding myself what are the things around it. Okay, let me make it prettier. So that's our final product. And we want to balance our chemical reaction, right? So we started using NaOH, and this one we're dissociating a Br minus. So our side product will be NaBr. And what's the name of our product here? So we have 6 carbon, so that is 1-hexyne. All right. Now, I want to ask you one more question. Does the reaction stop here, given that we have excess of the haloalkane under basic condition? Yes?
What happened to the water, like the OH that combined?
Oh, yeah, actually, that's a good point. But water, if we consider it a solvent, you don't normally write it out. So in this case, the reaction does not stop here. Because after all, when we're talking about chemical reaction, once you put the reactant in the test tube or in your flask, it will do whatever it likes. It will continue to react with whatever reagent you have until it reaches a point that nothing else can happen. So in this case, we were talking about the acidity of your hydrogen attached to the sp3 carbon. So in this case, we still have one more acidic hydrogen that can be further deprotonated and involved in subsequent reaction. So this is again a acidic hydrogen. So what does it mean? It means that under the reaction condition, we will further deprotonate it with a OH minus. And we'll be forming again a carbon-centered anion at the terminal position. And then we have 1, 2, 3, 4, 5, 6. And that's going to react with another molecule of your haloalkane. Same kind of arrow pushing. We're pushing it onto the carbon and the bromine left. And we're forming our product as well. Let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my carbon 1 is forming a bond with carbon 7. I'll sort out the numbering later on. So we end up getting something in the middle. So this is going to be my 1, 2, 3, 4, 5, 6, and carbon 1 making a bond with 7, and 8, 9, 10. Or what's the name of this one? Now we counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have a triple bond on the 5 position. So that's 1, 6, 5, 4, 3, 2, 1. So this is my 5-decyne. All right. So what is the take-home message of this reaction? A few things. First of all, it's under basic condition. We are utilizing the acidity of the sp carbon-hydrogen bond. We're utilizing the acidity of this hydrogen. Under basic condition, we're forming the conjugate base of acetylene that can act as a good nucleophile to react with the electrophilic site of a haloalkane. The take-home message here is this reaction is very useful because we are alternating the carbon skeleton, meaning like we started from molecules with less number of carbon, right? So in this case, we started from molecules with only 2 carbon, and then in the haloalkane with only 4 carbon. But eventually, we're making a longer carbon chain using the nucleophilic substitution reaction. The other take-home message here is if we start from acetylene, the reaction does not stop at the terminal alkyne because this terminal alkyne CH can be further deprotonated and undergo a second nucleophilic addition to form your final product, which is an internal alkyne. And again, if you think about this reaction, this is only going to work with primary, rewind. This reaction only works for primary alkyl halides, and the reason behind that we'll discuss in chapter 9. So for now, just remember this nucleophilic substitution reaction only works for primary primary alkyl halides. Yes.
So is it really uncommon in general to have terminal alkynes?
Or the other way to put it is this reaction requires a terminal alkyne to have that acidic hydrogen. So this one is a primary alkyl halide. And we'll talk about why it is the case in chapter 9. At this moment, just know this reaction only works for primary halides. Yes?
In that last step, you talked about a partial negative charge on the carbon, and it's continually being attracted to the partial positive on carbon 7. Why, if we have positive sodium charges floating around the solution, why is it not attracted to the positive?
Well, the way to think about it is your sodium plus is floating around. But again, this is an acid-base equilibrium, right? So your salt is not forming actual bond with that anion. It's like in your NaCl solution. It's not holding as a NaCl bond. That's an ionic bond. That's not a covalent bond that's going to last long. Now, your sodium is going to float around, but it's not going to form a covalent bond with the conjugate base of your acetylene. So this goes back to review of acid-base chemistry. Yes?
So why is it energetically favorable to form a really long carbon chain? Is it a typical?
Well, there's no real energetic penalty to form a longer carbon chain in this case. Okay, so in this case, the reaction takes place because we have this is a nucleophilic substitution reaction. I don't have the numbers on the top of my head, but you're forming new carbon-carbon bond and you're breaking a carbon-bromine bond. Now your carbon-bromine bond is a weaker bond comparing to your carbon-carbon bond. So in this case, there's no real energetic penalty to form the new carbon-carbon bond versus a carbon-bromine bond. All right. So this is one reaction, first reaction. We're exploiting the acidity of the acetylene hydrogen. All right, first reaction done. Next reaction. How do we form internal alkynes if we don't want to use that kind of strong basic reaction? So this reaction is called dehydrohalogenation from internal alkenes. So the overall reaction we care about is we start from an internal alkene, whether it's cis or trans, plus Br2, and under the condition of 2 NH2, and then form the product of H3C-A-alkyne and 2 HBr. So in this case, we're trying to solve what is the reaction mechanism for this reaction. So what do we know about it? The statement saying we're talking about knowing that treatment of a vicinal dibromo alkane, so a vicinal dibromo alkane is effectively saying we have two bromine group right neighbor to each other. So the statement is telling you treating this molecule with two more of base, which is given here, the 2 NH2 minus, into successive dehydrohalogenation reaction will form an alkyne. So that's like what we tell you, this is a new reaction that we have. But before we jump into the new reaction, how do we form the vicinal dibromo alkane? This is something we already known in the alkene reaction, right? So this one is a halogenation of alkene. So the first part of this reaction is more or less a review. So our first step is thinking about my Br and Br. We do an arrow pushing here to form that bridged intermediate. Right, so you have the bridgehead intermediate, and notice like if the substitution on my alkene is different, we have selectivity based on the stability of the carbocation. And then we have the second bromine group come and attack the carbon that does not have the bromine, or the carbon that has more carbocation character. And we're gonna form our intermediate, which is the vicinal bromine. Or your bromine groups are next on carbons right next to each other. Yes?
If you do the bromine cis to each other, would it be wrong?
Well, this should be anti to each other. That's the stereoselectivity we went over. Now, in this case, it doesn't matter because you have free rotation over the single bond. So I'm not going to deduct point for it. But if we're looking at the actual chiral molecule, then you want to keep in mind, like they should be anti to each other. Yes.
When you were saying that it was abridged, could it also, I remember we were talking about like major and minor. Why would this one be bridged and not like the other one?
I just didn't bother to draw all the structures. So this one, I'm just saying like the charge is delocalized over all three atoms.
Oh, okay.
Yeah, it's actually like three resonance structures contributing to this bridged intermediate. All right, and from here, this is what we know. This is reaction number 1, which is a halogenation of an alkene. This is something we already know. Next reaction is the dehydrohalogenation. So when we say a dehydrohalogenation, we're saying in presence of a very strong base. This strong base will come and grab the hydrogen, and then the electrons in that carbon-hydrogen bond will go onto the carbon-carbon bond, and then the bromine group will leave. So it's a consecutive process of reducing this vicinal dibromo alkene to a double bonded species. right? So in this case, if you're thinking about what's gonna be the product from this arrow pushing, now we're cleaving the CH bond. The carbon-carbon single bond becomes a double bond. The carbon-bromine bond is broken, and we're releasing a HBr. So this comes to carbon-carbon, Br, CH3, hydrogen, CH3. And the reaction can happen again. We still have a neighboring bromine group that can be, that can undergo the dehydrohalogenation reaction. So doing the same kind of reaction. So we have NH2 minus, and that grabs the hydrogen, the CH bond, electron in the CH bond go onto the triple bond, the double bond to become a triple bond, and the bromine leaves. All right, so the result here is our final product, which is a alkyne with 2 HBr. Or the overall reaction is showing on the top. You start from an alkene, reacting it with a molecule of Br2, and then under the treatment of strong base, NH2 minus, two molecules of the NH2 minus strong base, and we're forming the alkyne product. Yes?
I'm a little confused, because isn't the hydrogen bond in that H2 and not the bromine? Like, the HBr, where does the HBr come from?
Well, so in this case, I'm just trying to balance the chemical reaction. In reality, it's going to be Br minus H plus, and then reacting that with NH minus, NH2 minus, and so on.
Okay.
I'm just balancing the chemical reaction. All right, and let's do this one more time just to practice what we did. Imagine you're trying to, or one of these questions could be, I give you this reaction starting from butene going to 1 butyne, and we ask you, what is the reaction mechanism for this reduction reaction? Not reduction, what's the reaction mechanism for this preparation of the 1 butyne? And what is the reaction condition for this reaction, and how to balance this reaction with good enough amount, was the correct intermediate and substrate and whatever things we need. So this is the kind of question that could appear in your discussion worksheet or your exam questions. So how to do this? Well, we're thinking about first observing what is the left-hand side and what's the right-hand side. And we see we start from alkene, we end up with a alkyne. And observe it, we have the same number of carbons. So we do not need to add any new carbon-carbon bond in this process, like new carbon skeleton in this process. Right, so what we know that we just went over, right? So we want to do the bromination. And the dehydrohalogenation. So, what is the mechanism? First step, we have Br, or reaction A. We have the alkene attacking the Br group, breaking it to form that bridged intermediate. Now, in this case, the carbocation will more likely to be in the internal position or the secondary position, comparing to that in the terminal position. Or if you draw out all the intermediates, right, so that's something we already discussed before. And then you have another Br minus comes in, add onto the more stable or major contributor of the resonance structure. And we're forming our intermediate. Right, so that's our vicinal dibromo alkyl intermediate. And then from here, we have two consecutive base the base enabled dehydrohalogenation. So we have NH2 minus, and thinking about what are the hydrogens it is grabbing. So the hydrogen it will grab is the hydrogen next to a carbon-bromine bond, or neighboring to a carbon-bromine bond. So for example, in this case, this one will grab this one. The CH electron goes onto the double bond, and then Br group leaves. We form the intermediate like this. And we have one additional bromine group that can undergo a second dehydrohalogenation by grabbing the neighboring hydrogen. And CH goes onto the triple bond and Br group leaves. And this gives me 1, 2, 3, and carbon. All right, and note that this one is a terminal alkyne group in which we have a very acidic hydrogen. So if we're looking at it, the second step will be a very basic condition. So super basic condition, and this is gonna undergo a deprotonation. So the final product from my second step is gonna be a alkynyl anion from my second step. And we need a third step, which is what we call a workout, or like basically we're trying to protonate this final one with treating of water. And that is gonna form my final protonated product, which OH minus is my side product. Yes?
What was the point of doing that whole last thing? Did we start with the CH? Like, we started with, you said the acidic CH, and then we deprotonated and reprotonated?
Right, so if you think about what is happening, now imagine you're actually in the lab, you're doing the experiment, you're trying to get 1-butyne as your final product. From my process A, what is the condition in my process A? That is just my treatment of Br2, right? So after process A, we are getting this one as our reaction intermediate. So after A, we're getting our vicinal dibromo species. All right, and then in my process B, we're treating the vicinal dibromo alkyl group with a strong base NaNH2 with excess NaNH2, or at least 2 equivalent of NaNH2. Now the product coming from the second step is gonna be 1, 2, 3, 4, and an anionic species and 2 HBr. So the reason the product coming from the second step in your reaction mixture, it must be the deprotonated one. Well, after all, it's an acid-base reaction, right? The molecule does whatever it wants in the certain reaction condition. So as long as your reaction condition is basic, this terminal CH group will be deprotonated. It doesn't matter what I want it to be. So that is why we want to have a third step, which is a workup with water to get my final desired product. All right, so these are the 3 steps leading to our final product. Yes.
When you're turning a double bond to a triple bond, will it always be through this revolution process?
I would say at this moment, yes, this is the only reaction we went over, which is the dehydrohalogenation. But I don't want to say this is the only possible way, because eventually you'll learn more reactions, right? So right now, yes. Yeah.
To add on to that, if this is the only way that we're always guaranteed like to get a deprotonated alkyne, so we'd always have to add water to reprotonate it, right?
Right, because I mean, for example, if you are using the dehydrohalogenation reaction to form an alkyne that happens to be a terminal alkyne, you need to work it up with water so that you're ending up with like a terminal CH, sp3CH, SPCH. But as a side note, there's one flaw in this entire mechanism that can lead to side reactions. Well, when we're talking about the dehydrohalogenation, keep in mind, we are talking about the deprotonation of a hydrogen that's next to a Br group. So if I draw that out, we have 3 different hydrogens that can undergo the dehydrohalogenation with NH2 base, with a strong base. So that is why when we're talking about this kind of terminal vicinal dibromo alkenes, on top of formation of the terminal alkyne, it can also form a side product, like a side reaction taking place. And that is the formation of an allyne. So an allyne, again, like the alkyne, you have one sp3 carbon that is in the center. But different from alkyne, you have 2 consecutive double bonds. Not like alkyne, you have a triple bond. And the structure of allyne is like these double bonds are perpendicular to each other between different carbon atoms. Now the question I could ask you is how to form an allyne from this starting vicinal dibromo material, or like in this one, we tell you like in this reaction condition, tell me what kind of side product might be generating and show me how it is being formed. So in this case, how it is being formed. Now it's the same thing, right? We have NH2 minus, and this is gonna grab this hydrogen, and this hydrogen got on here, and we're leaving one of the Br group. What we're forming here, well, is a double bond, hydrogen, Br, hydrogen, hydrogen. All right. And likewise, we still have one hydrogen neighboring to the Br group. And we'll do that again. We're grabbing this hydrogen. Let's go to the single bond, and then the Br group left. And we end up getting a allyne group. All right, so like the alkyne, when we're drawing it as an allyne, you want to make sure you draw it as a linear molecule. So take home message here, how to prepare an alkyne. So either we start from an acetylene, so whenever you have a reaction that the carbon skeleton is being like manipulated to become longer, right? So you can start from a acetylene, reacting it with a primary haloalkene or a alkyl halogen through a nucleophilic substitution reaction. Or we'll start from an alkene, treat it with Br2 and then strong base to get this internal alkyne. if you do this kind of dehydrohalogenation with a terminal alkyne, there is a possibility of forming the allyne as a side product. Yes.
How difficult would you say this midterm is compared to the last one?
I don't know. I haven't write it yet. don't panic too much, right? I haven't write it. But this midterm too is going to be very focused on reaction. So get familiar and get ready to draw reaction mechanism, predicting products and predicting reaction conditions and so on. All right, I'll see you next lecture.